In part 1 we saw how the rings on a piston engine work. Now let's transfer that to the rotary. In a piston engine, all sealing surfaces are in a two-dimensional plane, but in a rotary it's three-dimensional with planes intersecting, meaning there's more gaps that leak. But the biggest kicker is the rotor travels slower than a piston. Simply put, a piston engine has to hold its compression for 180 crank degrees from top dead center to bottom dead center, whereas a rotary has to hold its compression for 270 crank degrees from top dead center to bottom dead center. And because gaps leak at a rate over time, and the rotor has to hold pressure for an extra 90 crank degrees, means that the extra time is going to allow the chamber to leak more. Basically, rotaries have more gaps to leak and more time for them to leak. This explains why rotaries have a low compression reading on the starter compared to a piston engine. First we'll look at the side seal, and this works like a compression ring in that it uses pressure differential to seal it. Combustion pressure presses on the seal, and the seal presses against the inside land of the groove, and it's the seating of the seal on the groove that produces the seal. If you look at the inside surface of a used side seal, you can see the shiny contact spots, and on the outside there's no contact except for a few spots on the bottom edge. This bottom edge mark is due to the combustion pressure tipping the seal. In an ideal world, the seal will press against the groove equally along its full length, but this is not what happens. Looking at the side seal again, we can see matte dull spots, and these are areas not making contact, and if continuous top to bottom are actually leaking. This is due to manufacturing inconsistencies because the side seal is roll formed out of a strip. That's one problem, but there's more. Ideally, the seal is pressed against the groove evenly, but when the rotor rotates in this direction, the friction of the side seal on the plate pushes the side seal in this direction. And because the side seal is not square to the corner seal, hence its angled end, it will climb up the corner seal until it reaches the other side of the side seal groove. And this makes a leakage path behind the side seal right here. You can see it more in the 1mm side seals, but it's this non-contact patch on the inside here. And when you flip it over, there's heavy contact on the outside on the trailing end of the seal. Mazda probably moved it off the centerline and closer to the combustion chamber so it reacts quicker. If you look at RX-8 rotors, they move the side seal even closer to the combustion chamber. This pushing to the corner seal is shown by a shiny spot on the trailing edge of the side seal and no contact on the leading edge, and a pressure mark on the corner seal, but only on one side. And it's this that stuffs up beginners who don't know how seals work. Side seals are supposed to have an end gap, but beginners think if they can make this gap smaller they'll make more power. So they force a feeler gauge into the gap, and this pushes the side seal to the opposite side of the groove. Then in operation, the side seals butt against the corner seals and lifts the center, and that produces a 150mm leakage path instead of the usual 0.05mm leakage path. Basically, if you've got a pressure mark on both sides of your corner seal, you're doing it wrong. Another thing about side seals is where they make contact with the rotor, they fret due to micro welding. Mazda probably keep their seals soft so they bend in quicker because it's not a very harsh environment for the side seals. As for side seal length, I wouldn't adjust them without some sort of jig, because it's very hard keeping the end square and having the right angle of doing it by freehand. I found this advanced setup, which is very similar to the jig we built to do piston rings. It's also easy to make a piston ring gap crooked when you're doing it by hand. You need a guide so the ring of the side seal meets the grinding stone at the right angle, and a control weight to feed the ring and side seal and measure it. That's what this dial indicator is for. If I see a rotor with twin side seals and has a blow-by recovery groove, I won't fit the inner side seals. Now let's look at apex seals. Again, this seal uses pressure differential to seal, so it's compression pushing the apex seal to the far side of the groove to affect the seal. We would like to think our apex seal is nice and flat to the groove, but in actual fact it tips away from the combustion pressure. But that's not the only force on the apex seal. As the rotor rotates in this direction, there's a friction force on the apex seal pushing it in the opposite direction, and this adds even more tilting force to the compression force on the apex seal. That's the trailing apex seal, but if you look at the leading apex seal, it runs like this due to friction until it's flipped by combustion pressure. And in the case of the leading apex, the friction is reducing the pressure of the apex seal on the groove. And that's why when you look at a used rotor, the trailing side is more flogged out than the leading side. If we look at Mazda's pressure difference between adjacent working chambers graph, when the apex seal is in a position where there's a high pressure differential between chambers, it'll be pushed against one side of the groove. But when the apex seal is in areas where there's not much pressure differential, friction will take over and push it to the back of the groove. Then on top of that they bore for the corner seal, and that doesn't leave much bearing area for the apex seal to rest on. And if we look at our apex seal down from the top, in operation the apex seal can flex and bend, and because it's resting on thin rotor land areas on the ends, it will flog out the apex seal groove ends a lot on the trailing side and a little on the leading side. These notch seals are more flexible and will initially make more power, but they wear out the apex seal groove faster, so they end up being worse than a solid type. Another problem according to Mazda is the seal sag in normal operation. Here we see roughly a 20 micron gap at idle, and this constant rubbing on the ends in low speed standard applications probably accounts for the edge grooves that you find in housings. On a side note, this 1981 book by Kenichi Yamamoto, they proposed pre-crowning the apex seals, but at 30 microns that would wear out in 3,000 kilometers. On the factory 3-piece 2mm apex seal, it uses a wedging effect to keep it flat against the groove, but that's on the trailing apex of the combustion chamber. On the leading apex it probably does the usual tilt. I think they induction harden the apex seal grooves in RX-8 rotors these days, so they're going to last a lot longer. Induction hardening of valve seats in cast iron cylinder heads has been pretty common for decades. If you're interested in the wear rates of standard Mazda factory parts, of the engines I knew the mileage of, 3mm apex seals wear at 0.1mm per 10,000 kilometers, so if your apex seals are 2mm shorter than new, you know it's done 200,000 kilometers. 2mm 3-piece wear at 0.08mm per 10,000 kilometers. Series 4 housings with 80,000 kilometers showed no appreciable marks on it, but at 110,000 kilometers I could see slight grooves on the edges. So maybe if you stoned your apex seals flat every 80,000 k's you wouldn't get grooves on the edges of the housings. As for mileage, I did 270,000 kilometers on my normally aspirated Series 4 engine and was quite tired by the end. I also had a customer do 300,000 kilometers on a 3mm apex seal engine, but that was freeway driving. Constant running engines like freeway cars and taxis don't wear out as quick as normal cars, because they are not subjected to as many heating start cycles. In the piston world, surface finish of the ring lands is very important, so in racing they lap the rings to effect a better seal. But the people at the time slotting rotors for 3mm apex seals didn't have a clue what was required, so they would push a 3mm slitting saw through the groove, totally destroying all the critical sealing surfaces. Rough surface finishes on apex seal grooves will wear out the groove faster, because high spots have less surface area and will flatten quicker. While researching pictures, I found an article where a guy's trying to re-chrome housings back in 2011, and this reminded me of when someone tried to do it down here in the late 90s. What they do is they bolt together 10 housings, dip it in wax, then scrape the wax off the inside chrome faces, throw the stack in the tank, then put an electrode down the centre and reverse electrolysis the chrome off, and then replate it with chrome again. If a housing had scratches, they had to smooth it out before rechroming. We had a customer supply some of these re-chromed housings, and after he refitted the engine, he went for a drive in the country to run it in. But by the time he came back in the afternoon, the engine was done. Upon inspection, there were scratches in the housings, and it looked like the apex seal was running on the steel sleeve that's cast in the housing that the chrome sits on. So I checked the thickness of the chrome and it was paper thin at 1 thou. Standard Mazda chrome is 4 thou thick. Mazda put down a base that's a slight gold colour, then a hardened chrome finish on the top that's always silver. So if you ever see a goldy colour in the chrome face, you've probably worn through to the softer base. I have salvaged housings where the customer couldn't afford new ones by honing the area with a soft dressing stick. All early 3mm housings were honed with a crosshatch, so I'm kind of duplicating that. The crosshatch grooves retain oil and that improves the seal, and this honing crosshatch is exactly what they do in a piston engine. Of course there's no guarantee once the goldy chrome is exposed. It looks like factory apex seals sag, but that's with normal combustion. Abnormal combustion is very different. We had a customer that couldn't start his car after he ran nitrous down the strip, and when we checked his apex seals, they were sagged in the middle, and it had bluing of the metal like you see on chrome exhaust pipes when they're overheated. We told him he was using too much advance, but he continued to do it 3 more times until it spat an apex seal. What happens is the seal gets very hot and then it expands a bit in the middle, and because the raised section is very hot, it becomes soft and wears very quickly. And because that section is now gone, when it cools down it shrinks smaller than before, and that makes a gap in the middle that leaks and makes it hard to start. Oddly enough, we used to see the same sagging phenomena with the white ceramic apex seals they used to make down here in the 90s, which is odd because you'd expect ceramic apex seals to be more impervious to heat. They also wore very fast and left flats on the crown of the apex seal. They look like these white seals here at the bottom. As far as aftermarket apex seals, I kind of left the scene just when they started, so I know about the white ceramic seals I think they used to make in Melbourne, and the later HME iron seals that used to come from England. The HME seals didn't break, but I noticed they were putting slight scratches in the chrome face in a short period of time. Researching this, I found an article by Rice Racing showing housings being destroyed by aftermarket apex seals. It's a hyped article with poor explanation, but at least it has some pictures. But again, it kind of shows backyarders with no engineering experience or knowing what they're doing, throwing stuff at the wall and seeing what sticks. Next we have the corner seal, and it has the most difficult job. Not stress-wise, but affecting a seal, because it has to seal in 2 different planes. Basically, it can't seal both planes effectively at once, so it does have a lot of leakage for its size. It has a leak at the side seal end gap, and because it can rotate, the apex seal can't rest on it and affect the seal, making a direct path from one chamber to the other. And if you use a solid type corner seal, it can't press on its own bore. That's why Mazda went with expansion type corner seals, so they can open up and seal on their own bore. They also have a leak at the bottom of the apex seal. Basically, the apex seal goes up and down, and if there's no gap, it would jam. Mazda tried to seal this gap by putting a flexible plug in their expansion type corner seals, but because it's some kind of soft synthetic rubber or silicone, it does have a limited life. With so many leakage paths, you can see why it's so influential in achieving a good idle. Lastly, we come to oil control rings. There's not much to say about control rings, just they're twin sharp-edged scrapers, with some sort of rubber-based O-rings to seal them, and that means the light green factory O-rings will swell if touched by kerosene. These rings need very smooth side plates to run on, or they'll smoke. And we did have a case with a set of plates that were surface ground too rough, so we had to hand lap them to stop the smoke. We swapped to a better plate grinder and didn't have that problem again. All Mazda seals are iron based and have the longest life in normal operation, but because they're iron based, they're quite brittle when pushed. And that covers all the seals.